Hi everyone, thanks for being here. My name is Dong Song. I'm a professor in computer science at UC Berkeley and also the founder and CEO at Oasis Labs. Today I will talk about AI and security, challenges, lessons, and future directions. As we all know, deep learning has made great advancements. For example, AlphaGo and AlphaStar have won over world champions, and deep learning is empowering everyday products. However, as we deploy deep learning, there's a very important aspect that we need to consider, which is to consider the presence of attackers for a number of reasons. First, history has shown that attackers always follow the footsteps of new technology development, or sometimes even lead it. And also, this time the stake is even higher with AI. As AI controls more and more systems, attacker will have higher and higher incentives to attack the AI systems. And also, as AI becomes more and more capable, the consequence of misuse by attackers will also become more and more severe. When we look at machine learning in the presence of attackers, there are at least two different types of problems that we need to consider. First, how attackers may attack the AI and the learning systems. Attackers can attack the AI and the learning systems in several different aspects. First, the attackers may attack the integrity of the learning systems, for example, to try to cause a learning system to not produce the intended or correct results. And attackers can even cause a learning system to produce targeted outcome designed by an attacker in a targeted attack. Attackers may also attack the confidentiality of the learning system to try to learn sensitive information about individuals from the learning system. To address these issues, we need to develop stronger security in learning systems. Another type of problem is how attackers may misuse AI. For example, attackers can try to misuse AI to attack other systems. For example, to try to find vulnerabilities in other systems and devise new attacks. And furthermore, attackers may try to misuse AI to attack people. For example, as what we have seen in deepfake fake news that have been generated that can be generated using learning systems. To address these issues, we need to develop stronger security in other systems, and also we need to develop methods to see how to better protect humans from these misuse of AI. Given the interest of time, in this talk, I will mainly focus on the first aspects of how attackers may attack the AI and the learning systems. And first, let's look at how attackers may attack the integrity of the learning system. To illustrate how attackers may attack the integrity of the learning system, let's first look at a motivating example in the domain of self-driving cars. An autonomous vehicle, as it drives through the environment, it needs to observe the environment, for example, to recognize traffic signs, and so that it can make correct decisions. Here are some examples of photos of real-world stop signs. And the second photo here is a real-world photo of a stop sign in Berkeley. And as you can see, on the stop sign, there are some marks and so on. But today's machine learning systems actually can work pretty well. For example, today's computer vision systems can recognize these stop signs quite well and correctly. But however, what if attackers actually try to manipulate these traffic signs, for example, by putting on specifically designed markers to try to fool the learning system to give the wrong answer? For example, instead of having the computer vision system to recognize these as stop signs, to try to fool the computer vision system to misclassify these traffic signs as speed limit sign and so on. And we call these attacks adversarial examples. These are essentially, for example, images that attackers have added specifically constructed adversarial perturbations to try to fool the computer vision system in this case. And in our recent work, we have also taken the study one step further to look at besides the fact that adversary examples can be effective in the digital world by adding perturbations to digital photos and so on, whether these adversary examples can also be effective in the physical world and also remain effective even under different viewing distances and conditions and so on. So in our recent work with my collaborators, we have shown that unfortunately the answer is yes. So what you are seeing here, these are photos of real world traffic signs that have been manipulated, where stickers have been added to these traffic signs, for example, in a specific constructed way, so that even for this physical object, when it's viewed from different viewing angles and distances, it can all cause the image classification system, in this case, to misclassify the stop sign into a speed limit sign, 45 miles per hour. And this example illustrates how attackers may attack the integrity of a learning system by maliciously perturbing the input to the learning system. And as you can see, this could cause severe consequences, for example, for self-driving cars and so on. And our constructed adversary example of a stop sign, a real-world adversary example, actually has been on exhibit in the Science Museum of London to help raise awareness for people to understand the limitations and the vulnerability of today's learning system. And that's just one example showing that adversary examples can be effective in the domain of computer vision and, in this case, image classification. But however, with our study and also many other researchers' study, unfortunately, we have shown that adversary examples are not just limited to image classification or computer vision systems. They are actually prevalent in deep learning systems. And we have studied adversary examples in different types of deep learning systems and in different domains, including generative models, deep reinforcement learning, and domains including visual Q&A and speech recognition and so on. And also, in particular, in addition to white box attacks, like what I just showed, where we assume that the attackers can actually know the details of the victim model, including the architecture and the parameters of the model. Black box attacks can also be effective, where the attackers don't even need to know the specifics of the victim model. For example, the attackers doesn't need to know the parameters or the architecture of the model, and the attack can still be successful. And we call this type of attacks black box attacks. And in our research and also other researchers' work, we have developed different types of black box attacks, including zero query attack, where attackers don't even have query access to the victim model, utilizing a capability called the transferability-based attack, where attackers can construct a local model and using white box attacks, attackers can construct adversary examples on the local model, and due to the transferability property, this attack, these locally generated adversary examples can succeed in attacking these remote models as well. And also with query-based attacks, attackers with query access to these victim models, such as through cloud APIs, attackers can also develop even more effective black box attacks. So now let's look at one particular example illustrating how effective this type of attacks can be, and using real-world cloud API services as examples. And also in this case, we also wanted to show that these type of attacks are not only effective in the, again, image setting, it can also be effective in the text domain as well. So here we look at how we can actually perform imitation training or imitation attacks of cloud APIs for machine translation, where by querying cloud APIs for machine translation, we can train an imitation model that is very similar to these cloud APIs that we call black box API models. And then we can show that by developing attacks on this locally trained imitation model, we can then also successfully transfer the adversary examples generated using the local imitation model to the remote model to have effective attacks on these cloud APIs as well. So first, let's look at how effective this model stealing can work. How well can we train the imitation model just through querying these cloud APIs? And in our case, we show that we can steal these models very effectively. And the trained imitation model can achieve very close performance matching these cloud APIs. And secondly, we explore different types of adversarial attacks on these machine translation models. And again, the attack works in two steps. So first, we developed various new types of attacks on the locally trained imitation models. And then we show that with high likelihood, many of these developed adversarial attacks can transfer to the actual cloud APIs. And the different types of attacks essentially are constructed by defining different types of loss functions, characterizing different types of attacks, and trying to solve the optimization problems with the given loss functions. So here are a few examples, types of attacks. One is targeted flips. So the idea is whether we can find attacks where by just simply replace an input token, we can cause a specific output token to flip to another specific token. So here's an example, translating from English to German. So the English sentence, the initial sentence is, "I'm going to freeze. It's now below 6 Fahrenheit. Please help me." And the machine translation in this case gives the correct translation. But however, by doing the attack, we are able to generate to generate this attack where we simply flip the 6 Fahrenheit to 7 Fahrenheit, and this will cause the machine translation to translate it into 21 Celsius instead of 7 Fahrenheit. And we show that when we input this attack example into Google Translate, Google Translate gives the same wrong answer. Another type of attack is malicious nonsense. Essentially, we start with the malicious inputs and replace tokens without changing the model's prediction. And the final result is a nonsense that actually can cause essentially malicious output. So for example, here we show that we can find this the nonsense sentence. When it goes through the machine translation, the machine translation will provide certain targeted outputs, such as "I have to kill you" and so on. And similarly, we show that these attacks also transfer into cloud APIs. And here's another type of attack that we call untargeted universal attack. It's a phrase that commonly causes incorrect translations when it is appended to any input. And here's an example. And also here's another type of attack that we call universal suffix dropper. It's a phrase that commonly causes itself and subsequent text to be dropped from the translation. So again, these examples illustrate that production NLP models, in particular in this case, machine translation, can be easily stolen, and also they can be easily attacked. And you can go to our website to find the code and paper as well. So again, what I have shown are just the tip of the iceberg. And for adversarial example attacks, there have been lots and lots of really exciting work. For example, there have been many diverse attack methods that have been proposed. And also, given the importance of the domain, numerous defenses have been proposed as well. Just in the last few years, hundreds of papers have been posted on arXiv proposing different types of defenses. But however, today, still, we don't have sufficient defense. Strong adaptive attackers today can still easily evade today's defenses. And again, this is just the tip of the iceberg. In general, the types of issues that I have been discussing about falls into the domain of adversarial machine learning. The domain of adversarial machine learning is about learning in the presence of adversaries. And and attacks can actually happen at different stages of learning. It could happen at inference time, where attackers can try to fool the learning system to give the wrong answer, such as the adversarial example attacks that I mentioned earlier. And also attacks can happen during training time as well, where attackers can try to poison the training data sets to fool the learning system to learn the wrong model. Overall, adversarial machine learning is particularly important for security critical systems. And I strongly believe that security will be one of the biggest challenges in deploying AI. So far we've talked about the first aspects of how attackers may attack the integrity of the learning system. And also attackers can attack the confidentiality of the learning system to try to learn sensitive information about individuals. Here, let's look at some concrete examples. And this domain is particularly important given that, as we all know, machine learning, although they are really data hungry, they are trained through a huge volume of data, and a lot of this data is really sensitive, and hence the user's data privacy protection is really important as we train and deploy these machine learning systems. So here is a concrete example illustrating why it's important for us to pay attention to protecting users' data privacy as we train machine learning models. So here's a recent work that we did in collaboration with researchers from Google. And here the key question that we set out to explore is, do neural networks remember training data? And if yes, can attackers actually exploit this to extract the secrets in the training data from just simply querying the learned models? So in particular, in this case, we looked at the task of training language models. So the task of training language models is by taking a corpus of text, for example, an email data set, then try to learn a prediction model where it tries to predict, when given a sequence of words or characters, it will try to predict the next character or word. So in particular, in this case, we studied the task of training a language model over a data set called the annual email data set, which naturally contained actual users' credit card and social security numbers. Our work showed that attackers, by devising new attacks from just simply querying the language model without actually knowing the details of the language model, including the architecture and the parameters, it can actually extract the original credit card and social security numbers that were embedded in the original training data sets. And these are examples illustrating that why it's important to pay attention to users' data privacy, even as we train machine learning models. Luckily, in this case, we have a solution. And the solution is that instead of just training vanilla machine learning model, instead, if we train a differentially private language model, we can still provide fairly high utility And at the same time, we can significantly enhance the privacy protection for users' data privacy. And differential privacy is a formal notion of privacy notion. In particular, we say that a randomized algorithm is differentially private if it satisfies the following property. We consider two neighboring data sets where one data set has one more points than the other data set, for example, Joe's data points. And when we compute the randomized algorithm or function over these two neighboring data sets, when we look at the computation results, the resulting probability distribution of the computation outputs, the two distributions are very close. And at high level, essentially, what this is showing is that by just looking at the computation outputs, the attacker won't be able to distinguish whether Joe's data has been included in the original computation or not, and hence help protect Joe's individual data privacy. And also our recent work has also developed automatic methods and new type systems to be able to statically enforce and verify that a machine learning algorithm is differentially private and provides provable bounds on its on the privacy guarantees. And the work has won the Distinguished Paper Awards at UPSLA, which is the top programming language conference. So what I have talked about in terms of protecting user privacy, in particular as we train machine learning models, that's just one example. And again, it's just the tip of the iceberg. As we all know, data is critical to the modern economy. But however, a lot of this data is really sensitive, and handling the sensitive data has posed unprecedented challenges for both individual users as well as businesses. Individual users have lost control over how their data is used, and also a lot of user data has been sold without users' knowledge and consent under the umbrella that the dataset has been anonymized, where certain personal identifiable identifier has been removed. But however, a lot of work has shown that anonymization often is insufficient in protecting users' privacy, like the recent New York Times article that has shown that they were able to track the location of a Secret Service agents with the President Trump from an anonymized data set collected from location data from mobile phones. And also users are not getting sufficient benefits from their data. And also on the other hand, businesses continue to suffer as well. For example, they continue to suffer from really large scale data breaches. And also it's becoming increasingly more cumbersome and expensive for businesses to comply with the regulations such as CCPA and GDPR. And even more importantly, it continues to be really difficult for businesses to utilize data due to data silos and privacy concerns. And also, as we develop new technologies that can unlock utility, it may also oftentimes come at the cost of privacy. And hence, we cannot continue with the current status quo. The current status quo hinders societal progress and undermines human values and fundamental rights. And hence, we have an urgent need for a framework for building a responsible data economy. Building a framework for a responsible data economy is a complex problem for a number of reasons. One, there's natural tension between utility and privacy. And also data is non-rival, meaning that data is unlike a physical object, where for a physical object, if A holds an apple, the same apple cannot be held by B at the same time. Whereas data, the same piece of data can be made many copies, and different entities can all hold the same data at the same time. And thus, we cannot simply copy the concepts and methods in the analog world to help address problems in the digital world. And thus, to build a framework for a responsible data economy, it requires a combination of technical and non-technical solutions. And in particular, it needs to have at least 3 components: the technical aspect, the legal framework, and incentive models. For technical solutions, we need to develop new technologies that addresses the insufficiencies from traditional solutions. In particular, we need to develop new technologies that not only protect data at rest or in transit, as the existing data encryption does. We also need to protect data in use and in compute. And also, we need to enable controlled use of data without having to copying the raw data, which will cause the data owners to lose control of their data. And furthermore, we need to be able to protect the computation output from leaking sensitive information about the inputs, as we have seen that, for example, anonymizing data often does not provide sufficient protection to privacy. And luckily, we have seen a really exciting and rapid advancements in different component technologies to enable responsible data use. This includes secure computing to try to help protect the computation process from leaking sensitive information, utilizing techniques and solutions such as secure hardware, as well as crypto-based methods such as secure multi-party computation and homomorphic encryption, and so on. And also differential privacy for protecting the computation outputs from leaking sensitive information about individuals. And federated learning helps the data owners to keep data on their local devices and machines, and enable different entities to together train a machine learning model in a distributed manner. And this can also help further protect users' data privacy. And with distributed ledger, it can help provide an immutable log to ensure the user's rights to data, and also how users and users' policy of how their data can be used, and also to provide an immutable log of the usage of the data. At Oasis Labs, we are also working in pushing forward these different component technologies, and also weaving together these different component technologies to enable a secure distributed computing fabric that can serve as a platform for a responsible data economy to help address many of the challenges that I mentioned earlier. As a concrete use case to illustrate the capability and the power of these component technologies and the platform for a responsible data economy, here let me give you just one example of a use case in genomics that we have been working on. In direct-to-consumer genomics, companies essentially collect users' genomic data and help provide genomic analysis results to users. But however, recently we have seen layoffs in these direct-to-consumer genomic companies, in particular citing privacy concerns of consumers as a main reason for a slowdown in consumer adoption. So in collaboration and in partnership with another genomic company, we are in the process of launching a product and service. When this is launched, this will be the first time where users can become owners of their genomic data in the sense that they can maintain control over their genomic data and how their genomic data is used. Their genomic data will be stored in encrypted form, and the users get to specify how they want their genomic data to be used. For example, they may allow a genomic company to provide genomic analysis of their data. But in this case, by utilizing secure computing, the genomic company will not get a raw copy of the user's data in this case, and the genomic company can, if the user allows the genomic company to run the analysis, the genomic company can run the analysis in the secure execution environments to provide the computation results to the user, but the genomic company will actually not be able to get a raw copy of the user's data in this case. And hence, users can maintain control of their data and still be able to utilize their data in a privacy-preserving way and in a controlled manner. Besides technical advancements, we also need more effective regulation as well for responsible data use. And there are many challenges in this domain. For example, what are data rights? Who controls data rights? Individual property rights are a cornerstone of modern economy and has helped establish modern economics and fueled centuries of significant growth. However, today we lack an adequate framework for data rights. Establishing data rights will allow individuals to derive value from their data and propel economic growth and unlock new value. And we need to explore a diverse set of concepts and frameworks in this domain. And in particular, we need to develop data-driven, technology-informed regulation. For example, how will advancement of responsible data technology influence and impact regulatory frameworks? And how can regulation help with the faster and broader adoption of responsible data technology? For the future of the internet, we must create a new ethos of responsible data. We need everyone to demand and enable responsible data. So to summarize, in this talk, I have talked about many open questions and challenges at the intersection of AI and security. For example, how to better understand what security means for AI and learning systems, how to detect when a learning system has been fooled and compromised, how to build more resilient learning systems with stronger guarantees, how to build privacy-preserving learning systems, and how to build a responsible data economy. And the work is in collaboration with many of my students, postdocs, and great collaborators. And again, I strongly believe that security and privacy will be one of the biggest challenges in deploying AI. And building a responsible data economy is critical. And this requires community efforts. Let's tackle the big challenges together. Thank you.